So, very briefly, I'd like first to start by telling a few words about this experience in response mode. They were mostly covered by Adam, fundamentally. You have to respond really, really quickly. There is, as Ellen pointed out, there is an issue with the size of the group. And I had the impression that Imperial and London School are in a much easier position in the sense that I suspect having 3 layers where you have really the top people that attend meetings like SPI-M and so on, and then some more junior researchers that are absolutely experienced enough to coordinate small projects, and then other students below them working, makes life a lot easier than for slightly smaller groups, like Ellen was pointing out, in the sense that well, I've been going from one meeting to the next, and so it was very difficult to attend the meetings and also coordinate any sort of research. So having only 2 of these 3 layers makes life a lot more difficult, and that's what Ellen pointed out. In general, there was an issue with the Adam covered very well in terms of struggling with the publication system, the peer review system that is not really set up to deal with emergencies. Yeah, and and I will talk very briefly about that. When you try to get a message out, then they say, "Oh, we want to listen to this message until it's peer reviewed," and then a month later, after the peer review process ends, then they say the peer review process says, "Well, this is already known." So that's the end of it. So it's a little bit stressful, and but understandably so. And we need better solutions. And in particular, one potential solution that has been suggested to me would be to have reviewers that are not necessarily involved in doing stuff, but are more involving into kind of reviewing stuff. And but of course, if you're not then rewarding them, if they don't get any career boost because they've not done anything, then it makes life a little bit challenging. But this I just thought that I might prefer to share later with the group. I personally had I struggled a lot in terms of I was asked to do things, and therefore the more you do, the less time you have to read, and that has played against me at times, and not only in terms of maybe redoing stuff that other people have done, but also other people know stuff or know about data, and then you're trying to reconstruct that data using models, and you worked on it for a bit, and then the data comes out, and then the model is obsolete, as Adam was suggesting. So it's absolutely, I completely sympathize with most of the struggles, and I've been, I think the fact that London School had a lot of experience from previous outbreaks has helped a lot. We have never really worked very much in response mode. I'm making these comments because they will filter through all the examples I'm going to talk about later. For example, using relatively simple models or instead of complicated models, and what the pros and cons are about this. There are lots of data issues that have been raised in the past. That means that in many cases, the impression I have is that if the data is too dirty, then there is an interest in working on really simple models. But at the same time, then the political questions require really complex models. And you do not know how to parameterize these complex models. And so simultaneously, we have a situation where if you want to do something that is robust on data, you need to use a simple model because the data is just not good enough to parameterize a complex model. But at the same time, there is a lot of scope to help politics by just using a complex model with parameters that you just vary. Okay, even if they're not informed by data, the answer obviously is going to be, if this parameter is big, you'll have this result. If this parameter is small, you'll have that result. And that does nothing more than just quantifying the intuition that you had at the beginning, and that you think everyone else around had, and possibly politicians or policymakers in general had this idea intuitively. But if you back it up with some numbers and scenario plannings, then they will be extremely grateful and happy with what you are saying, even if it's nothing else than putting some numbers that to you mean very little, because they are not rooted into anything, they're just pure assumptions. And how these numbers can actually inform, well, can just attempt to quantify the intuition that they had. Basically, they would like to act, and they can't only act on intuitive ground, and they would just like, they really need or have a lot of appetite for models that do nothing else than confirming the intuition they had through some numbers. Obviously, you should be very careful as a modeler that that intuition is not wrong in the first place. But most of the time, the intuition is not wrong. It's just that they really want you to say, oh yeah, but just put me a table with some numbers to show this. And so I was really surprised about how helpful models can be, even if they are out of the blue type of numbers. Briefly, I would like to talk about the current work that we're doing in Manchester, and then some further discussions on other models that we have handled in the past, and then challenges. Current work, so fundamentally, there are 3 of us in Manchester. It's Ian Hall, Thomas House, and myself, and we are broadly covering 3 different branches. So Ian Hall is mostly involved in care homes and is coordinating the care home, the national response in terms of care homes. And the problem with care homes is that the data is still, it's getting better, but it's still pretty weak. So it's very difficult to say something proper about care homes. And these, you can try to plot these graphs where the dots is not even like number of cases or anything. It's literally like number of care homes that have reported having an outbreak of a size that could be anything. And it's only one point in time. This is just the times at which care homes report something. And then you can try to infer what the general trend is. As you can see, even accounting for weekend effects in reporting and stuff like that, I mean, you have something that goes up and then kind of remains stable, and you don't really know what that really means. On the right-hand side, it's an attempt to plot an instantaneous growth rate. And you can see it was fast at the beginning and then it slows down. So this is one thread. The second one is Thomas House, who's working quite a lot on ONS data, Office for National Statistics. They are really very careful about showing any sort of data. So I can't really show any graph on this. And I'm not even really able to comment very much on what Thomas is doing in detail. He's also working on growth rate and households networks, contact tracing and stuff like that. You can ask Frank Ball, because he probably knows much more than I do at the moment. And then Thomas has his fingers in many pies, so I'm not really sure what else he's doing. But mostly he's doing some stats in the ONS data, which is very much needed at the moment. And then I focus mostly on short-term forecasts, and I might be coming back to this later, but fundamentally I have a model of flow in hospitals. Susceptible individuals get infected, and they are either asymptomatic, and we know very little about asymptomatic people, or they are symptomatic. There is an early asymptomatic phase. It could be either with no transmission, like a proper incubation period, or it could be early low transmission phase. It doesn't really matter. And then some people end up recovering, some people end up in hospital. And one of the attention we paid in this model is to separate infected people in those that will end up recovering and those that will end up going to hospital, because the rates of moving across this in these paths can be very different. For example, this is effectively, say you are infectious for 7 days and then you recover. This is one thing. If instead you get infected and you have symptoms such that you need hospital, then maybe you go to hospital within 2 days. So separating already compartments based on the route you're going to take next seemed to us a really neat trick for deciding, for accounting for timing of events a bit better. And the same trick is used later. If you end up in hospital, you can end up in hospital but will eventually die, or you end up in hospital and will require critical care, or will end up in hospital and recover. Okay, and those that end up in hospital with critical care, then split in those that will seek critical care but then will eventually die, and those that will seek critical care and then recover, and then they might step up into a monitoring phase in hospital and so on. But basically the rates in different paths can be very different, and the data is really supportive of that. And so separating in these compartments was one way of accounting for that. Okay, and then this model is used to do the short-term forecasts. Twice a week, we are asked to do some forecasts of what's going to happen for the coming 2-3 weeks. And from these forecasts, we also try to find some values of the reproduction number. And the struggle is that there are lots of different data streams, and it's not very easy to link all of these data streams in a neat format. For example, in this case, I'm using data streams about hospital incidence, hospital prevalence, ICU prevalence, and deaths only in hospital. But then I do not really know how to account for deaths in the community, because my community aspect of the model is really weak. It's not particularly informed by data. That's because we don't really observe much of the transmission in the community. And so how can you use deaths in the community if you do not have a component of the model that accounts for it? I know, for example, Public Health England is focusing more on the deaths data. So it's able to capture most of the deaths in the community. Well, it's using data streams about deaths in the community, but then they can't really link that to hospital. And so you're basically fitting to deaths and predicting deaths. And there are other groups that fit to hospital and predict hospital. And it's very difficult to link the two, in my opinion. This is one of the main challenges. And so these are some graphs where I have removed completely the numbers, so so no one can moan that I'm showing any data that cannot be showed, because no one knows what this data means here. But it's just some ideas about what sort of models, what sort of short-term forecasts I'm doing. And you can have in red, for example, this is the new hospital admissions, the deaths in black, and the hospital beds in blue, and the ICU beds in light blue. And then as you can see, it's not really necessarily that easy to fit models like this, because the data can be very noisy. And depending on which data stream you're fitting, you get different results. For example, if I was only fitting to ICU data, I would see that now the situation should be really flat. And if I instead account for hospital prevalence, then I would predict something goes down. So some of the inconsistencies, or the difference, if you want, in predictions from different groups and different models that are reflected in very large intervals in what is reported in the media, are down to these things. Different groups have different models, and they have different, they are fitting them to different data streams, and the result can be quite different. For example, if I were only deciding to fit for the last week of data, then I would predict something flat, basically, by looking at these points. But if I take into account that this is coming down, has been coming down consistently for weeks, then I have a slightly different idea, right? And I attribute the rest to noise. What is noise and what is signal? It's an open question. It's really difficult to kind of disentangle the two. So this is current work. In the past, what we have been really working on strongly in the past was, early on in the epidemic, no data stream was particularly reliable. And the impression from previous studies from China was that the doubling time was more on the order of 5-6 days. But when the epidemic started spreading in Europe, then it became quite obvious that things are growing much faster. The problem is that it was very difficult, because every single data stream is biased. And so we thought that maybe combining data streams and combining multiple regions was the best chance of saying that things are actually doubling every 3 days rather than 6, which is an important message. And then we submitted this, and it was told to us that it's already well known, and after a month, then it's completely outdated as a piece of information. So this goes back to the struggles we were having, but these struggles are also due to the fact that the data is what it is. Like, for example, what can you infer from Greece? These are a number of confirmed cases, by the way. It's not even clear what a confirmed case is. But try to fit an exponential growth to Greece, you just don't know what to do. There are other countries where the situation is better, but of course, some countries like Italy started much earlier on, and then you were in a situation where control policies were implemented really quickly, so the growth just changes over time, while in other countries the growth was still kind of unconstrained. And so it's just a little bit problematic to find something that is simultaneously not cherry picking, and at the same time that is indicative of what's happening. Yeah. So this is a plot, but on a log scale. And again, you can try to fit what you want, but then also the window in which you're fitting is completely determines what your conclusions are. For example, there was always a good example. Say the growth I observe here in Poland obviously is affected by these 2 data points. But if I exclude those 2 data points, I will get something that goes much higher, right? So even that is just problematic. And the data, especially the daily data, is incredibly noisy. So another alternative is to use generalized additive models. So that is basically assumes that you have a growth rate that changes over time, and it changes over time. Instead of allowing just to change freely, you just fit a spline, a cubic spline to that model, to that growth rate that changes over time. And so you get something that does change in time, but it's a little bit smoother than just allowing every week to be different, right? So even that proved quite complicated. For example, German data seems to be oscillating a lot. You can remove something by, you can get something easier, something simpler to see if you remove Saturdays and Sundays, but that's again, like how much of this is cherry picking and how much of this is doing something principled, right? So one of the key messages for why the growth rate was actually faster is that deaths and confirmed cases, you don't know what confirmed cases are. Deaths might be affected by the fact that older people and more frail people die sooner. So then that seems to be growing faster at the beginning of the epidemic. Then both of them are biased. But then if you start adding hospitals as well, and at the beginning hospital data was only published by Italy, you had, you can see how the confirmed cases, the ICUs and the hospital data are all with a doubling time of around 2-3 days. And that is, and that was another strong piece of evidence that the signal we were saying is really a signal and not just a consequence of biases in the data. Also, it's clear that the biases in the data, if you start swabbing crazily, you get the number of confirmed cases going up really quickly because they depend on the speed at which you swab. But how much of that is, well, that's due to the speed at which you're swabbing, and you want to clean that kind of signal, but how can you do that if you do not have any other data stream? Crucial in some of the messages of this particular piece of work, it was not only that the numbers double every 3 days, but also that the incubation period is around 5 days, which is what it was known, and we just used a slightly more sophisticated method, but we got to similar results. And then onset, from onset of symptoms to hospitalizations or to confirmation, you get another 4 or 5 days. And that means it's 9-day delay between infection and actually appearing on any statistics. And that corresponds to 3 doubling times. So this means that by the time you act and you try to see the effects of what you're doing, numbers are growing by a factor of 8 at least. And that's kind of consistent with countries, multiple countries having this issue where the numbers are low. You start imposing one sort of control policy, numbers keep on rising. You have, for example, you have closed schools, so you have suggested social distancing, and numbers still keep growing fast, and you do not know what to do. You just think your control policy is not working, so you ramp up control policies one after the other, because that's all you can. That's all you can do, really. And numbers keep growing further and further because it still takes a week, 10 days minimum to start seeing effects of what you're doing. And then by the time you see the effect of what you've done and you introduced 4 different control policies, then you're in the situation where you're like, so which of my control policies have worked and what's the effect of the different control policies? And then you don't know which one to relax because you were unable to estimate the effect of them. And in particular, you might think that the final control policy is what brought the numbers below 1, when in fact it's possible it was the previous one. It's just that you're only seeing a delayed effect of it. And then the last one maybe added a tiny bit on top of it, but it wasn't like the game changer, if you want. Yeah, there was, I was also involved in the same manuscript. We also comment on the fact that the estimates of R0 vary really widely in the literature, and it's really unclear whether this is due to the fact that they are fitted to different data in different settings, or how much is due to the fact that they're fitted maybe to the same growth rate, but you are making different assumptions on the amount of pre-symptomatic transmission. For example, this is the incubation period for different individuals. Say this in yellow, there is the infectivity profile of different individuals. This can be very variable. If you then decide that your transmission starts 2-3 days sooner, then for the same growth rate, you get a much lower value of R0. And so it's possible the discrepancies between R0 also depend on which individual study is assuming what about pre-symptomatic transmission. And because estimate vary widely, and Adam was talking about the fact that there is evidence there is quite a lot of it, but it's very difficult to pin down properly, then this partly is reflecting into the variable estimates of R0. But fundamentally, what we were pointing out in this manuscript is that even if you know R0 exactly, then you will still struggle because you do not know by how much you change R0 if you enforce or suggest social distancing, because you have no idea about the response of people. And this is an issue that crops up also in terms of predictions. Fundamentally, I have the impression that most of what we do is trying to make sense of the current state of things rather than predicting anything.
Right. Lorenzo, can you wind up there?
Yeah, one last thing probably. I have a few more slides that we can discuss later about more complicated models, in particular households models, that have been worked out really early on, but that's the parameters were really difficult and are currently very difficult. There is very little information that I know of, and partly it's my fault, about within household transmission. And contact tracing is also on the forefront, but I discussed that. We've been working also on the risk of introduction in prisons, and that's again back to the challenges of informing, quantifying the intuition that other people might have, but they really want a number for a number for R, and you're trying to tell them that this number means absolutely nothing. If it's 1, but you have 100 cases per day, then you get really low risk of importation. If it's 1 and you have 10,000 cases per day, then you have a much higher risk of importation, and R is still 1 because numbers are constant over time. And there is a lot of scope for explaining this to other people. I think I commented on some of these graphs, but the challenges are enormous. One last thing I want to say is that I've heard many people, there was a discussion between the deterministic and stochastic models, and this might be of interest to this audience. And lots of people were saying, oh, we need to quantify uncertainty properly. And I completely agree with that. It's really, and so I've heard people saying there is no, we should not really provide any policy support unless we quantify uncertainty properly. And I agree with that message. But at the same time, when doing this model fitting, I was realizing that the fitting the data is really difficult. And therefore, if my median predictions are wrong, and my median predictions might depend on some assumptions I've made in the model, for example, when I'm assuming the parameters might be changing, whether I'm assuming the parameters might be changing at certain point in time or not, what I consider noise and what I consider signal, can impact my median predictions. And if my median predictions is rubbish, then there's no point in having really sophisticated models that inform a confidence interval around it. And the only example is here, for example, if I'm not allowing the model to change the downward slope. So here I change beta, the transmission rate here, well, a bit before the peak. So there's delay and then numbers go down. And then I change beta roughly here, or a bit before this other bend. If I don't do that, then the model will predict a downward slope, which might be also sensible given this last bunch of points, okay? But then if I allow beta to change, then the hospital data is kind of forcing the curve to pull up, and therefore I'm getting a slightly different slope at the end. So my predictions of the reproduction number are very different between here and here. If I do not allow that change, my predictions of the reproduction number and my forecasts will be completely different. And this is not an issue that only accounting for stochastic or proper uncertainty quantification is able to resolve. This is a model choice, And to a certain degree, it's the distinction between what I consider is a signal and what is considered is noise. And I think with that, I'm closing. Sometimes it's even more difficult, like what's the signal here, for example. And in other cases, you might not even have all the data streams you want. So these are some of the challenges I face, and I hope these are helpful for any further discussion. Over.
Okay, thanks very much. I think, unless there are any burning questions, we should move straight to general discussion.